Okay, we're now ready to talk about hole cleaning, which is basically the nitty-gritty, getting down to what we actually do in the ADT service and how we apply all the stuff we've just been learning together to monitor for hole cleaning efficiency on a job using PWD and other tools. So after completing this module, you'll be able to list the primary factors which affect hole cleaning, describe the consequences of poor hole cleaning, describe cuttings bed formation, describe what's meant by critical flow rate, describe the various factors involved and discuss their relative importance, and also you'll be able to suggest ways of improving hole cleaning without stepping beyond the constraints of the system. So let's have a look at a pictorial representation of a well bore. Most of this discussion that we're going to go through here will involve this particular profile of well, mainly because we've got a vertical section, we've got a reasonably high-angled inclined section, and we've got a horizontal section. So we'll talk about all three of these sections while we're talking about hole cleaning and compare cleaning in each of them. If you have a look, the constraints on this well bore are the upper constraint would be the fracture gradient or the rock strength. The lower constraint, the pore pressure, as in if your hydrostatic or your circulating density comes below the pore pressure, you'll take a kick. If it goes above the fracture gradient, you break down the rock. We've got a blue dashed line here, projected ECD. That's projected by a model, by your hydraulics models. And then you've got PWD data. Over the top of that, you compare the real-time PWD data with the model, and as it varies from the model, you work out what's actually happening down the hole, based on some of the knowledge I'm about to give you. If you look at a cross-section of the hole, when you're drilling the well bore, you'll find that often you'll have cuttings beds building up. Now here we've got a cuttings bed shown with the pipe here, the borehole here, and basically a bed of cuttings which the pipe is kind of nestled within. And there's a cuttings bed height shown on here relative to the pipe size and the borehole size. So we'll talk about cuttings beds, where they form, where they're most likely to form, how easy it is to clear them out, and so on throughout the rest of this presentation. But before we actually go on to hole cleaning itself, talking about hole cleaning itself, we have to actually work out what a cuttings bed is. So we have a look at this film here. This is a cuttings bed. It's a bed of cuttings on the low side of the hole. Kind of obvious really, but just so you can actually see what it looks like. We've got a perspex tube here. It's about 5 inches in diameter, and it's got a rotating pipe on the inside, which is about 2.5 or 3 inches in diameter. And these are limestone cuttings of various sizes being injected at the bottom, and you can see a bed formation. The bed is forming on the low side of the well bore. And the well bore is inclined, so we're actually looking in this case, we're looking at this sort of area of the well bore here, 65 degrees, that is. Basically, so a cuttings bed is a build-up of cuttings on the low side of the hole. It restricts flow. As you can see, it's taking up some amount of the well bore, so it's restricting the amount of flow through that. It's restricting flow through the well bore, making the annular diameter less than it would be if the well bore was clean. And it's also increasing torque and drag. As you can see, if it's coming up over halfway, then the pipe's going to be stuck in these cuttings. And if you try and pull the pipe up or down, or even rotate it, you're going to have to increase the amount of torque for rotation. You're going to have to pull harder or push harder, or basically slack off more weight to get it to move through this sort of thing at the bottom of the hole. So what are the consequences of inadequate hole cleaning? Well, basically, there's an inability to continue drilling. Well, if you don't do anything about it, you won't be able to drill any further because the torque will increase too much. You'll also probably increase the variability of the torque, or how erratic that torque is. So you'll have a big fluctuation in torque. It could lead to stick slip as well. You'll end up with an increased drag on connections, and increased drag on trips and so on. So it's going to be far harder to pull out of the well bore, and also quite difficult to get back in with new BHAs, also casing and so on. So if you don't attend to it, you won't be able to drill the entire well to TDE. You can also break down the formation in some cases, because if the ECD increases due to the build-up of cuttings, then you may end up actually increasing that ECD beyond the fracture gradient. And that could actually happen gradually if cuttings just build up very slowly as you're drilling on, or if you've got a build-up of cuttings during sliding, when you start rotating and these cuttings are lifted into the annulus, you can get a sudden increase in ECD that just pops you over the fracture gradient and immediately get a pack off and start losing mud. So you can basically break down the formation. You'll have difficulty maintaining directional control with a motor or with adjustable gauge stabilizers or with geopilot. If you're not cleaning the wellbore correctly, you'll have difficulty actually moving the pipe in the direction you want to go. And in the end, you'll end up with stuck pipe. Stuck pipe is a major economic burden, as it says here, on oil companies. That's why we get put on stuck pipe courses very often in the North Sea. It's one of the more common, for a long time it was one of the more common problems down the hole. And a lot of stuck pipe problems come from bad hole cleaning practices. Okay, so what are the factors that actually affect hole cleaning? Well, the following factors affect hole cleaning. You've got flow rate, for one. Rheological properties. You've got basically your viscosity of your mud, your gels, and so on. Cuttings density, cutting size, cutting shape. Fluid density as well, as in fluid density will affect it, because fluid density is what gives you buoyancy, which will lift cuttings. As well as rheological properties like viscosity will also help to lift cuttings. Rate of penetration, ROP, that's basically how fast cuttings are being generated. You've also got hole angle, as in different angles, but as we'll find out, different angles are harder to clean than others. Borehole eccentricity, which is a symbol epsilon. We've talked about that before. That's how far off-center the pipe is within the wellbore. It can be concentric or it can be totally eccentric, so it can go from 0 to 1, basically. Pipe rotation and pipe reciprocation, as in moving the pipe around and lifting it up and down. That's basically going to help with cleaning. We'll find out how much it might help and where it might help in a short time. Now, looking at the first of those, flow rate, symbol Q, it is the single most important parameter when considering hole cleaning. And I can't stress that enough. If you talk to our friends in Bayreuth, they actually go around the world troubleshooting hole cleaning problems when they've been unable to drill wells in certain areas. And when they look at it, a lot of the time the wellbore has been planned with things like sweeps and rotation and wiper trips and all sorts of secondary means of dealing with hole cleaning problems. But when some of these guys actually have looked at the data, they found that the flow rate that was being used was actually just not enough to clean the hole in the first place. So it's the single most important parameter when considering hole cleaning. Without enough flow, we can adjust all the other parameters we like, but we will always have problems regardless of what we do. We might be able to improve things, but we will always have problems if we don't have enough flow. So when we're designing a well, the flow rate in the annulus needs to be high enough. That's something I want you to remember all the time when you're looking at a hole cleaning job. Flow rate needs to be high enough. Okay, so what flow rate is actually high enough? Well, basically, if we have a look at this, we've got cuttings beds forming, but they're basically forming dunes. And as you can see, the dunes pretty much form and they roll up the wellbore. We've got saltation of the grains over the top of them. We're pretty close to what this critical flow rate actually is. And the critical flow rate is the rate below which stationary cuttings form, stationary cuttings beds form. Now, stationary is the word here, and this is critical flow rate for hole cleaning, not critical flow rate for, it's not like critical velocity and annular velocity for turbulent and laminar flow. It's got nothing to do with that. This is a critical flow rate below which stationary cuttings beds form. Now, if we fall below the critical flow rate, let's watch what happens. Okay, basically here we're significantly below the critical flow rate, and what actually happens is cuttings just fall to the bottom of the hole. They start slumping back down the wellbore. You still get a little bit of saltation across the top of that cuttings bed, but it just keeps building up and building up. And if you're in a high angle wellbore, these will just slide down. As you can see, they're beginning to slump down. Even although you've got grains going over the surface, the whole thing is actually tending to slip down. And if you can imagine that wellbore with the vertical section, the tangent section, the horizontal section, all the way down the tangent section, if you're below the critical flow rate, you're building up a bed like that. It's just sliding down and then collecting at the bottom. So that's what the critical flow rate is. Now basically, what is high enough? Well, with most muds, and I stress here muds, as in fluids with viscosifiers added and weighting material added, we need about 180 feet per minute in 12¼ inch hole. And we can probably expect problems if it's less than 160 feet per minute as an annular velocity. And we will almost certainly have bad problems at less than 120 feet per minute in the annulus. In an 8½ inch hole, we need somewhere between 150 and 165 feet per minute. Now these are rules of thumb, and as I say, they're with mud. Now if we actually look at, we'll look at a film here of cuttings being pumped, cuttings being moved up the wellbore, and we'll attempt to see the point at which we cross the critical velocity threshold, where we actually stop beds being formed. But we'll actually be looking at it with a base fluid, because the base fluid is a lot clearer and it's a lot easier to see cuttings in than a mud would be, which is pretty opaque really. So one of the consequences of having a base fluid is that it's got very, very little viscosity. Therefore, it's not got a lot of carrying capacity. So the critical velocities in the annulus that we end up having to achieve will be much higher than they would be for most muds. But regardless, the principles are the same. So we've got a hole angle of 65 degrees, cuttings production rate of 20 pounds per minute. That's what we're putting into the bottom of the wellbore all the time. It's in 5-inch hole with pipe rotating at 50 RPM, just holding a constant rotational speed. And as I said, we'll see that the annular fluid velocity needs to be much higher with the base fluid than with the mud. But we'll be able to see the principle in action. So looking at this here, what we've got is a flow tube, and it can be raised or lowered to different angles. Set it at 65 degrees, pumping up here at 200 gallons per minute, which equates to 252 feet per minute as an annular velocity. Now looking in at the cuttings, we can see that we've basically got a thick bed on the bottom of the wellbore here at 200 gallons per minute or 252 feet per minute. That bed isn't being cleaned out effectively at all. So increasing the flow rate to 220 gallons per minute, which is 277 feet per minute, zooming in a little bit on the pipe, you can see you're getting a lot of cuttings moving across the top of the bed, but we're still not effectively cleaning that bed out. It's still relatively thick. I mean, we're getting in there through the bed porosity, getting quite a bit more in the way of cuttings coming out at 220 gallons per minute. Still not enough though. It would still give you a heck of a lot of torque and drag in a wellbore that was as unclean as this. Moving on to 240 gallons per minute, 302 feet per minute, we start to clean this bed out with the extra velocity. But what you'll find is we're still actually getting beds which are forming dunes, which are rolling up the wellbore. And when you switch your pumps off, they'll all just slump to the bottom. And so there's still a danger for torque and drag, stuck pipe and so on. We're cleaning the wellbore more efficiently though. It's still not beyond that critical velocity. Now if we increase to 250 gallons per minute, that's near the critical flow rate. We can see that we've got a very thin bed on the bottom. We've got these dunes going up. The dunes aren't particularly high. Whenever they get above a certain height, they were just getting the top chopped off them. So we've got a thin layer of cuttings. Again, not totally effectively cleaning the wellbore. When your pumps go off, you've still got this thin layer on the bottom. You start pulling stabilizers, your BHA up through that. That will drag all of this up the wellbore with you, and eventually you may end up with a pack-off situation if you stick your pumps on. So you'd probably have to do a little bit of circulation and a little bit of pipe reciprocation on the way out of the wellbore if it was long enough and you dragged up these cuttings. But very close. It's a lot better at a higher flow rate. Now increasing by just a further 5 gallons per minute, you've got 321 feet per minute. Now you've got the odd, you'll see the odd bed just appearing but then disappearing instantly. And there's never any definite layer of cuttings along the low side of the hole here. And we're basically, there's no cuttings beds present. There are clumps of cuttings. If you suddenly increase your ROP briefly, a clump of cuttings will go up, but it's still getting cleaned effectively. It's not stationary for any more than an instant. So there's no cuttings beds present at 255 gallons per minute, which equates to 321 feet per minute in this particular annulus. So as you can see, you basically, once you go beyond the critical flow rate, you still get clumps of cuttings moving up the wellbore, but they're never stationary for any length of time. But below it, you start off with a very thin skim of cuttings on the low side, which could cause you problems on a trip out. Significantly below it, and you've got large dunes, and then even further down, you've just got a huge clump of cuttings that is just an even spread, filling up a third of the wellbore, half of the wellbore even in some cases. Okay, how can we actually improve the flow rate? Well, simply put, we can either reduce the annular clearance or we can pump faster. Reducing the annular clearance means drilling a smaller hole or putting bigger pipe into the same size hole. Now we've got to remember that we've got certain constraints on the pipe weight. So we put in larger pipe. Our hoisting capacity is going to be the upper limit of the pipe weight that we can suspend. And when we're down in a deep, long hole, there's only so much pull we can put on that whole system. There's an upper limit to what we can lift. So we put in larger pipe, we're putting in more weight. So we've got to bear that in mind. It's a limiting factor. And also, there's a maximum standpipe pressure, which is a limiting factor for your pump rate as well. So we can reduce the annular clearance and pump faster by using larger diameter pipe. Increasing the pipe size, as I said, increases the loading on the surface equipment. A larger pipe, smaller annulus, higher pressure in the annulus. Also, if the ID is increased because the pipe's bigger, then you could end up with higher pressures internally as well. And basically, as I mentioned previously within this course, there is a type of drill pipe that's actually been specifically designed for hydraulic optimization. That's 5 7/8 pipe. And it has the following advantages. Basically, it reduces the annular size, giving better velocity. As I've mentioned, reduce that annular size, same volume going through it will go through faster. It also has a larger ID, which provides an increased flow capacity with a less pressure increase. So if the ID of the pipe is larger than, say, normal 5-inch pipe or 5.5-inch pipe, then the pressure drop within the pipe, which is the main part of your standpipe pressure, if you remember correctly, the pressure drop within the pipe will actually be less because the ID is larger. It'll also give you less loading on your hoisting equipment than, say, 6 5/8-inch pipe, which is one of the common drill pipes that they use instead of 5-inch pipe to increase the annular velocity. But the 6 5/8 is pretty heavy pipe, and you can't drill 8.5-inch hole with it because the annular clearance is so small that it actually it's far too high an ECD with 6 5/8 pipe in 8.5-inch hole, which basically means if you drill your well with 6 5/8, you've got to swap out that drill pipe for 5-inch or something else when you get down to your 8.5-inch section. Whereas if you drill your upper hole sections with 5 7/8, you can still go on and drill your 8.5-inch hole section with 5 7/8 as well. Just show some of that graphically, briefly. If you actually have a look at this graph here, if you look at the 6 5/8, there's two, we've got the internal string pressure and the annular pressure. Now the annular pressure in 8.5-inch hole here, the annular pressure for 6 5/8 is incredibly high, as you'd expect, because you wouldn't be normally drilling with 6 5/8 in 8.5-inch hole. But it's prohibitively high, so you wouldn't be able to drill with that. The internal string pressure is the lowest on this graph. Meaning that the standpipe pressure down to the pressure down to the bit, down to the BHA within that pipe is really low, and it's not going to be inhibitive at all. But it's the annular pressure that stops you from drilling with 6 5/8 pipe. If you look at the other common increase in pipe size, you've got 5.5-inch pipe. Now the 5.5-inch annular pressure is nice and low down here. this light blue line down here, the 5.5-inch string pressure, it actually, it's reasonably high. So you're going to have an increase in standpipe pressure here at 1,200 gallons per minute, which is pretty high for 8.5-inch hole, I must admit. But when you're down here, you've got getting on for 1,500 to 2,000 psi at the length of pipe that I put into this equation, obviously. So 5.5-inch pipe, although it reduces the annular clearance, it doesn't reduce it that much, so you don't get a great deal of extra annular velocity, but what you do get is an increase in standpipe pressure. So the 5.5-inch isn't really optimum in this case. But the 5 7/8 pipe, if you have a look at the internal pressure and the annular pressure, there are two green lines on here, and they both basically sit at approximately the same level on the graph. So the internal and annular pressure, when you're drilling 8.5-inch hole, neither of them are prohibitive at all. So it's actually the optimum pipe size for drilling an 8.5-inch hole, and it's better in the larger hole sizes as well than normal 5-inch pipe, or even 5.5-inch pipe, because you've got a larger annular clearance. And because the internal pressure is significantly lower than the 5-inch pipe, or 5.5-inch pipe, you can physically pump a lot faster through it as well without getting your standpipe pressure up there.